decimal triangle inscribed in it. Say this one A, B, C, where this B is sort of midpoint of the arc. That's what we have in the parabolic situation. In the parabolic situation, if this was a parabola, Archimedes would say the arc of the parabola is 4/3 the area of the circle. Wouldn't it be nice if there was some constant like 4/3, but some different value, that works for the circle? But he was not able to find such a thing. In fact, he was not able to find any kind of easy relationship between these two areas. Okay, that's sort of the reality of it. The reality is that this fundamental difference between the calculation of Archimedes for the parabolic arcs and the calculation of Archimedes for the circular arc, this separation is hugely important in the history and development of calculus and our theoretical understanding of it. Okay, so there's a gap. There's a separation that I want you to really think about. The separation between the parabolic area problem, there's a parabola, cutting off a piece, we're interested in finding the area of that parabolic piece. We can do that. Archimedes teaches us how to do that. Exactly, precisely. So not only is it a question of something that we can calculate, but it's more importantly something that we can define. We're able to define what we mean by the parabolic area. That's what Archimedes' calculation is really allowing us to do. But opposed to that, there's a big gap between this other situation with the other kind of conic sections, the circle and the hyperbola. So here's the circle, and here's the hyperbola. We'll talk more about these things in a future video. So here's a piece of a circle, and here's a piece of a hyperbola. And the same problem does not have a precise answer either in the circle case or in the hyperbola case. We are not able to do what we're able to do over here. All we can do over here is get approximate values. We can get intervals. You say, we work hard to get there's an interval. The area of the segment, whatever it is somewhere inside there. And someone else can work harder and get a smaller interval and say, I've got it now within a smaller interval. And then you can go away and work even more and more and more and more, and you get a smaller interval. But that's all that anybody ever can do. That's somehow the mathematical limit of what you're able to do. You're never able to actually get an exact value. But we pretend that we can. Yes, we have this elaborate real number fantasy story involving lots of letters and such. It's symbolic, but allow us to believe that we can get at these numbers, but the reality is that we can't. Okay? And it's important for us to look at this reality head on, not shy away from it, to really try and to really come to grips with it. So this is very important, and it's going to be a theme that runs through the calculus. Very important theme for the algebraic calculus. Now, Archimedes' thinking was the forerunner of many other works in this direction. So this is a very central problem of trying to estimate the area of the circle of radius 1. And Zhu Changxi, who lived from 429 to 501, a Chinese mathematician, used a 24,576 gon, which was 2 to the 13, so taking the hexagon and dividing it up another 12 times. And he was able to obtain this beautiful estimate. Pi is roughly 355 over 113, and that's to decimal 3.1415929. And all the way up to there, it's actually agreeing with modern calculators. So it's very impressive. Al-Kashi, almost 1,000 years later, in 1424 in Samarkand, came up with this beautiful formula for 2 pi, 6.16.59.28.01.34.51.46.14.50.01. And that may look like a very kind of funny number, but that's a number in the Old Babylonian second decimal system. So that's with base 60. So it starts with 6, and then 16 over 60s, 59 over 60 squared, 28 over 60 cubed, etc. And it turns out when converted to decimals, that it gives this value here, which is correct up to 6.4 there, and then it also gives these two values, but they're not in agreement with modern values. So our view is this one here, going up to the 6.4 and then 7.6. And then we might mention, amongst many other people, more modern European mathematicians who have tried to calculate pi. L. von Ceylen from the Netherlands in 1610 spent a huge amount of his life calculating pi to what turned out to be 35 decimal places. And he used a polygon also with many sides. This was 2 to the 62 sides. So it's a very fine spline, okay, with 2 to the 62 sides, and he's computing probably circumferences, and was able to get pi to 35 decimal places. That took him many, many years. Since this is such an important calculation historically and theoretically, we want to also attempt to get at the area of a circle. But we're going to have a different point of view in two different ways. First of all, we're not going to assume that there is a well-defined notion of area. And we're going to take a more applied point of view, and maybe a less ambitious point of view, and restrict ourselves to the idea of trying to get approximate areas, very much along the lines of Archimedes. So we're going to find inscribed circular splines and circumscribed circular splines, but it's going to be different from most of the historical precedences in that we're not going to look for regularly spaced ones. So we're not going to think in terms of angles and subdividing angles. Rather, we're going to think about what's called a rational parametrization of the circle. So but before we do that, we need to become a little bit more familiar with sums and some summation issues. And we also want to say a little bit something about tangents, because we need an understanding of tangents to get at the circumscribed circular spline. But we're going to come back to this problem, something that we're going to flag, and we're going to show you how to calculate the approximate area, or maybe approx area of a circle in a somewhat novel and maybe more efficient way than most of those historical examples that we've been talking about today. So there's much to learn. I'm Norman Waldberger. Thanks for listening. I'm Norman Pablo Arbiter, and welcome to Algebraic Calculus. In today's lectures, we want to look at an important formula having to do with sums of powers. We're interested in summing things. That's essentially the heart of the integral calculus. And we're going to be interested in summing areas of polygonal regions first, and then summing areas of curved regions. So these formulas, the ones on this page, and generalizations are going to play an important role in that. The first formula is a very familiar one, I hope, that the sum of the numbers 1 plus 2 plus 3 all the way up to n is n times n plus 1 over 2. These are the triangular numbers, like 1, 3, 6, and 10. For example, if you add up 1 plus 2 plus 3 plus 4 plus 5, that's altogether 15, and that can be expressed as 5 times 6 over 2. Now, in this case, there's an easy geometrical explanation for that, because this sum can be represented by this region here, the red region, with the area of 1, 2, 3, 4, 5. And then if we juxtapose that with an equal region, the green one, with area 1 plus 2 plus 3 plus 4 plus 5, then they match up to form this rectangle of side n times n plus 1. In this case, 5 times 6. And that's why the individual sums are half of the product of n times n plus 1. Now, this important formula goes back to ancient Greek times, well known to Euclid. Then Archimedes discovered an extension of that formula to sums of squares of natural numbers. 1 squared plus 2 squared plus 3 squared all the way up to n squared is n times n plus 1 times 2n plus 1 over 6. And if you haven't seen this formula before, you might like to check it for some small values of n. Then a few hundred years later, Nicomachus discovered this formula for the sum of cubes. That 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed is n squared times n plus 1 squared over 4, which remarkably is exactly the square of this one. So if you want to add up the cubes, say from 1 cubed, 2 cubed, all the way up to, say, 10 cubed, that's exactly the square of the sum 1 plus 2 all the way up to 10. Beautiful formula. Okay, so these are important formulas for a wide variety of applications, but they're very, very important for calculus, both historically and conceptually. And what's really interesting is how to generalize these formulas for higher powers. That is, how do we go to powers of, say, 4, or 5th powers, or 6th powers, or more generally to kth powers? That's an important question that we're aiming towards answering. But before we do that, we should backtrack a little bit and just talk a little bit about summation notation, which is an important tool that allows us to deal with adding up things in a kind of an efficient way, especially when those things are arranged in a relatively organized fashion. So summation notation involves this Greek letter, this capital sigma. Sigma is like an S, and the S stands for sum. So the sum from I equals 1 to n of a sub I. What does that mean? Well, it means that we're supposing that we have some sequence a sub I. So objects, typically numbers, but maybe also polynomials or anything that we can add. And there's an A1, and there's an A2, and there's an A3, all the way up to some a sub n. And this means we're going to add up a sub 1 plus a sub 2 plus a sub 3 and so on, all the way up to a sub n. The sum from I equals 1 to n of the a sub I. So the index here, the I, is a kind of placeholder. It does not actually figure in the final result. It just allows us to keep track of what things are being added to get the total sum. So the bounds here, the numbers 1 to n, which bound the start of the sequence and the end of the sequence, should be natural numbers, and typically we want the first one to be less than or equal to the second one. But things are flexible, so sometimes we go from 1 to n, sometimes we might want to start from 0. A lot of counting is a little bit easier to start with 0. Okay, so here's some examples just to show us how this works. The sum from I equals 1 to 3 of I cubed. When I is 1, we get 1 cubed. When I is 2, we get 2 cubed. When I is 3, the final one, we get 3 cubed. And the sum of those things is 36, as you can check. Here's an example where we use a different index rather than I. We don't have to use I. We can use j or k or anything else. So the sum from j equals 2 to 5 of j minus 1. So the j minus 1 is in brackets here, making sure that we're going to sum all of those things, not just the j's. So when j is 2, we'll be told to compute 2 minus 1, which is 1, and add it to the sum. And then when j is 3, we get 3 minus 1, or 2. When j is 4, we get 3, and when j is 5, we get the last entry, which is 4. So this is another way of writing 1 plus 2 plus 3 plus 4, which is, of course, 10. Now, the bounds don't necessarily have to be specific natural numbers. They can also be variable natural numbers, in which case we don't get a number as an output, we get a polynomial typically, or some kind of expression involving that bound. So, for example, the sum from k equals 1 to n of k to the 5th. Now the bound is an n here, which is variable. It can change. We can even think of it as being a polynomial. Okay, so when k is 1, we have 1 to the 5th. When k is 2, we get 2 to the 5th, and then 3 to the 5th, 4 to the 5th, and so on, all the way up to n to the 5th, which is the final one, whatever n is. So this is just a way of writing this. It's really a polynomial in n, degree 5. Another important special kind of case is when we're just summing a constant. Let's sum from I equals 0 to 6, the number 1. Now, this 1 here does not have an I dependence. So that means that each time, as the counter ticks over from 0 up to 6, each time we're adding 1. That 1 is not changing. It doesn't have to change. So when I is 0, we have 1. When I is 1, we have 1. When I is 2, we have 1. When I is 3, we have 1. 4, we have 1. 5, we have 1. When I is 6, we have 1. So altogether, we have these 7 1s, and so the total is 7. So now we can re-express these sums of powers that we're interested in, and also to do some notation for them. So let's denote by S1 of n the sum 1 plus 2 plus 3 and so on all the way up to n. In summation notation, that's the sum from I equals 1 to n of I. Okay, the I itself is changing. When I is 1, there's 1. When I is 2, it's 2. That way we go through the sum. Now this particular sum, we know what it is. It's n times n plus 1 over 2. And then S2 of n is the sum of the squares from 1 squared up to n squared. And here it is in summation notation. Summation I equals 1 to n of I squared. And we know what that is as a function of n. It's n times n plus 1 times 2n plus 1 over 6. And there's 3 then, the sum of the cubes. There's summation I equals 1 to n of I cubed, and there's the formula for that. And here then is the general formula that we're actually interested in, s sub k of n. So k is another natural number, and we're talking about the sum of all the k powers of natural numbers, starting with 1 to the k, then 2 to the k, all the way up to n to the k, and adding them all up. In summation notation, here it is right here. Summation I equals 1 to n of I to the k. So I is the index, the dummy variable, if you like, that's running through our range from 1 to n. N is the limit, the final value, and the actual power that each one is being subjected to is k. It's I to the k. Now, our suspicion is that, following from the pattern here, this is probably a polynomial in n. In fact, it's a polynomial in n probably of degree k plus 1. This is quadratic, this is cubic, this is quartic. It seems to be almost one more than the power. And we'd like to know, what is that polynomial? How does that polynomial depend on k? K equals 4, what is it? K equals 5, what is it? K equals 6, what is it? K equals 100, what is it? So this summation notation is a very efficient way of dealing with adding up quantities, but there's some rules that we need to learn. There's also some conventions that we need to be specific about. So the first rule is how to take the sum of two sequences. So suppose we have one sequence, A1, A2, A3, A4, etc., up to some value A sub n, say, and we have another sequence, B sub 1, B sub 2, B sub 3, up to some value B sub n. And here on the left-hand side, we're talking about the sum from I equals 1 to n of AI plus BI. Okay, so that whole thing, when I is 1 is A1 plus B1. And then when I is 2, we have plus A2 plus B2. And then plus A3 plus B3, all the way up to plus AN plus BN. And what this rule is saying is, somewhat obviously, that this is the same as the sum of all the A's. The sum from I equals 1 to n of AI, plus the sum from I equals 1 to n of BI. So it's a kind of associativity with respect to this summation notation. A few remarks to make. Notice that we're not putting brackets around here. You might think that we should put brackets around here, but we're not going to, because we're going to adopt the convention that this sum extends, but doesn't include like a plus sign. Like that. So it extends up to there, but that plus sign means that now we're talking about something different. And that's also the reason why we had to put brackets around here, because if we didn't put brackets around here, then this would be interpreted simply as the sum of AI, that sum, the moment that sum is finished, then plus BI, whatever that means. It would be then a somewhat ambiguous kind of thing. So we are obliged to put brackets around there. That's something that students often are forgetful of, so please keep that in mind. Similarly, there's a formula for the difference. Summation AI minus BI is the summation of AI minus the summation of BI. And then here's a distributive property, that if we're summing C times AI, and now C is just a number, a constant number, crucially, that does not depend on I. So it's the same, it doesn't change. So what this really means is the sum starting with C times A1, and then add C times A2, add C times A3, all the way up to C times AN. And that common factor of C can be pulled out front, and the rule is telling us we're getting C times the sum I equals 1 to n of AI. Notice that in this case here, the summation is such that this product has precedence over the sum, so we would calculate this product first. We don't have to put this in brackets. That's our agreement. And finally, kind of a special case, sum I equals 1 to n of 1 is equal to n. All right, so if there's no dependence on I, that just means that you have to add that same thing to itself as many times as the index runs over. In this case, there's n values, and so we get this number 1 added to itself altogether n times, for total n. So some simple but important rules that allow us to apply the summation notation to more complicated expressions. Now, before we get to the sums of powers that we're interested in, there's two other very fundamental and elementary kinds of series that we want to investigate, and one of them is the arithmetic series. So let's start with the idea of arithmetic sequence. Sequences and series are different things in mathematics. A sequence means that you list a bunch of numbers or variables or some other quantities, one at a time, separated by commas. And there's no actual arithmetical operations involved. We're just listing things. So here's A1, A2, A3, all the way up to A sub n. That's a sequence. Now, such a sequence is called an arithmetic sequence if it has a very strong property. If the terms of the sequence have this constant difference property. So here's the rule. That A2 minus A1 is the same as A3 minus A2, is the same as A4 minus A3. All consecutive differences are equal up to the very last one, which is A sub n, minus the previous one, which is A sub n minus 1. Okay, so this n minus 1 here, that's the index. The index there is 1 less than that index there. So we're requiring that all these differences be equal, let's say, equal to some common difference value D. Okay, it follows then that the kth element in this sequence is given by the expression A sub k equals A1 plus D times k minus 1. Let's look at that. So when k is 1, this will be 0, and we'll just get A sub 1. When k is 2, we get A1 plus D. That's consistent with the fact that A2 is D more than A1. And then as we bump up the k, we're adding one more d each time. So we start with A1, and then A1 plus d, A1 plus 2d, A1 plus 3d, all the way up to the final one, A sub n, which will be A1 plus n minus 1 times d. So that's the sequence. Now the associated arithmetic series. So a series is what you get when you add up elements in a sequence. The arithmetic series is A1 plus A2 plus all the way up to AN. So we're just taking the sequence and adding up all the elements. In summation notation, that's summation k equals 1 to n of A sub k. And now because we have this expression for A sub k, we can put that in with brackets. So summation A1 plus D times k minus 1. And now we can manipulate that a little bit. We can write it as summation k equals 1 to n of a1 plus the summation of this. And since there's a common factor of d, I'm going to pull that d out at the same time. Write it as d times summation k equals 1 to n of just k minus 1. So I'm using two rules. I'm using the first rule about how to take the sum of a sum, and then also how to deal with a constant, a common factor. Now this sum here, sum k equals 1 to n of a1. This is an a1, not an ai. So it means we're adding a1 plus a1 plus a1 all together n times. So we get n times a1. And here, there's going to be a d times, what is this sum? This is the sum of the numbers from starting with 0, 0 plus 1 plus 2 plus 3, all the way up to the last term will be n minus 1. Well, that's exactly that first power sum, S1 we called it, that was known to Euclid. But now it's going from the numbers 0 up to n minus 1. That means that the answer is n minus 1 times n all over 2. That's a triangular number. So that's a formula for the sum of an arithmetic series. So it turns out that this can be rewritten, and in the worked examples, I show you how to do that. It's relatively simple, that this can be rewritten in a pleasant way in this form, that it's also n times a1 plus an over 2. In other words, you take the first element in the sequence and the last element in the sequence, and you take their average, thing that's halfway between, and you take that average and you multiply it by n. So adding up the series is the same as taking just the average of the outside elements and multiplying that by the number of elements in the sequence. So you might like to just verify that yourself. So that's arithmetic series using a bit of summation notation. Now let's look at the other important kind of elementary series, which is a geometric series. So first of all, a geometric sequence, a1, a2, up to an, is defined by the constant ratio rule now. We had constant difference rule for an arithmetic sequence. Now we have a constant ratio rule for a geometric sequence. And what this is telling us that is each element in the sequence is a common ratio or common multiple of the previous one. So a2 over a1, this ratio, is the same as the next ratio, a3 over a2, which is the same as the next ratio, and so on, all the way up to the last ratio, which is an over an minus 1. And this common ratio that figures in each one of these is, let's say, r. That is what a geometric sequence is. Alright, so if we have such a geometric sequence, then the kth element in this sequence is a sub k, which is a1 times r to the k minus 1. Why is that? Well, a sub 1, there it is, and then a sub 2 is going to be r times a sub 1. So it's going to be r times a sub 1. And then a sub 3 is going to be r times a2. In other words, it's going to be a sub 1 times r squared. And then it'll be a sub 1 times r cubed, a sub 1 times r to the fourth, all the way up to the last element, which will be a sub 1 times r to the n minus 1. So we have a good control over the elements in a geometric sequence. And now the associated geometric series is what you get when you add up the terms in the geometric sequence. So we take this sequence and we add up all the terms. We get a series, a1 plus a2 plus all the way up to an. In summation notation, here's what it is. Summation k equals 1 to n of a sub k. We're using the dummy variable k here because, well, we've just written the kth term in terms of k, not I. And we know what this kth term is. It's a sub 1 times r to the k minus 1, so we just plug that in there. And now we can simplify this a little bit because that a1 is a constant. It doesn't depend on k. So it can come out front. We're getting a1 times summation k equals 1 to n of r to the k minus 1. So now this sum here is, when k is 1, we have r to the 0, which I remind you is 1. So it's 1, and then plus r squared, plus r cubed, and so on, all the way up to the final term, r to the n minus 1. And then it's an important sort of exercise to evaluate that geometric series, and we get r to the n minus 1 over r minus 1. And the worked examples, I'll show you how to do that. But it's good for you to think about it yourself if you don't already know. And it's an important caveat that this does not work when r is equal to 1. So it's valid when r is not equal to 1. If r equals 1, this formula couldn't really work because we have 0 over 0, which would be meaningless. And you might like to think what happens when r equals 1. All right, so we have a good understanding of summation notation. We have some familiarity with the important arithmetic series and geometric series. Now we're in a position to tackle this very important 17th century problem of how do you get control over these sums of powers? How do we get at this s sub k then? This, what we think is likely to be a polynomial. Well, that engaged the minds of quite a few 17th century mathematicians. A fellow called Faulhaber came up with the formulas first. Pascal thought about this, and Jacob Bernoulli really sort of nailed what was going on. And so we're going to present that in our next video. So there's much to learn. I'm Noah Wahlberger. Thanks for listening. I'm Norman Wahlberger, and welcome to Algebraic Calculus. In this lecture, we're going to pin down the sums of powers formulas that go back to Faulhaber and also to Jacob Bernoulli. So basically, we're interested in this kind of series. Sk of n equals 1 to the k plus 2 to the k plus all the way up to n to the k. In summation notation, sum I equals 1 to n of I to the k. And the exponents here, the k's, are natural numbers 0, 1, 2, 3, etc. And we're